Have you ever looked at a world map and noticed something peculiar? How the coastlines of continents, especially Africa and South America, look like they could just fit together? Well, that simple observation sparked a massive scientific question. Are the Earth's land masses and oceans fixed in place, or are they constantly, almost imperceptibly, on the move? Today we're going to trace that revolutionary journey, from the early hunch of continental drift all the way to the modern comprehensive theory of plate tectonics.
So, here's our game plan. We'll start with the big picture idea of our planet as a dynamic, changing system. Then we'll dive deep into Wegener's Continental Drift Theory and the mountain of evidence he gathered. From there, we'll see how that idea transformed into the theory of plate tectonics. We'll even zoom in on the specific, incredible journey of the Indian plate. And to wrap it all up, we'll sharpen our focus on what all of this means for the UPSC examination.
You know, the whole story really does begin with that simple jigsaw puzzle observation. For early scientists and cartographers, the uncanny symmetry of the continents bordering the Atlantic wasn't just a quirky coincidence, it was a clue, a hint that perhaps these vast landmasses weren't always separated by an ocean.
And this leads us to the fundamental question that really drove geological science for decades. For centuries, the default assumption was that the Earth was static, unchanging. But the evidence, bit by bit, started telling a different story, a story of a dynamic world where continents wander and oceans open and close. So the question is, how did we go from a suspicion to a scientific certainty?
The first person to put all the pieces together into a single, comprehensive theory was Alfred Wegener, a German meteorologist, back in 1912. He put forward the theory of continental drift. The idea was radical for its time. He proposed that all the continents we see today were once joined together in one enormous supercontinent, which then broke apart and drifted to their present positions.
Wegener gave names to the key players in his grand theory. The supercontinent he called Pangaea, which simply means all Earth, and this massive landmass he proposed was surrounded by a single colossal ocean he named Panthalassa, meaning all water.
So how did this great breakup unfold? Well, Wegener suggested that roughly 200 million years ago, Pangaea began to crack and split. The first major break created two new supercontinents, Laurasia to the north and Gondwanaland to the south. But it didn't stop there. These two giants continued to fragment, eventually giving rise to the familiar shapes of the continents we know today.
Now, an idea this revolutionary couldn't stand on just a map fit alone. It needed hard evidence, and Wegener was meticulous. He pulled together compelling data from completely different fields, geology, paleontology, even climatology, to build an undeniable case for his theory. Let's walk through that evidence.
He really built his argument on four main pillars. The first, of course, was the jigsaw fit of the continents. The second was finding rocks of the exact same age and type on coastlines separated by thousands of kilometers of ocean. The third was startling evidence of ancient glaciers in what are now tropical regions. And fourth, the very peculiar distribution of certain fossils and mineral deposits.
Let's get a little more specific. Using radiometric dating, geologists found that ancient rock belts, about 2 billion years old, on the coast of Brazil, were a perfect geological match for those in Western Africa. It gets even more interesting. Ghana has rich gold deposits, but there's no source rock for the gold nearby. Where did it come from? Well, these deposits line up perfectly with gold-bearing veins in Brazil. It's like finding a trail of breadcrumbs that leads across an ocean.
The climate evidence is just as powerful. Tillite is a very specific type of rock. It's formed from the debris left behind by glaciers. Now, geologists found these Gondwana system tillites in India, Africa, South America, Antarctica, and Australia. The only way you get glacial deposits in places that are now deserts or tropical rainforests is if those continents were once huddled together over the South Pole. It's a fossilized footprint of a completely different world map.
And maybe the most famous piece of evidence comes from fossils. Meet the Mesosaurus, a small reptile that lived in fresh water. Its fossils are found in only two locations on the entire planet, South Africa and Brazil. Now, there's just no way this little creature could have swum across 4,800 kilometers of saltwater ocean. The only conclusion that makes any sense is that South Africa and Brazil were once joined.
So, With all this incredible evidence, why wasn't Wegener's theory immediately accepted? Well, it had one huge, glaring weakness. He couldn't convincingly explain what force was powerful enough to move entire continents. It took decades, and technologies developed after World War II to find that missing piece and upgrade his idea into the full-fledged theory of plate tectonics.
This was the question that stumped everyone. Wegener himself proposed a couple of ideas, a pole-fling force from the Earth's rotation and tidal forces from the Sun and Moon. But physicists quickly did the math and showed that these forces were millions of times too weak. They couldn't push a continent an inch, let alone thousands of kilometers. The mechanism just wasn't there.
The real breakthrough came from a geologist named Arthur Holmes in the 1930s. He proposed that the engine was hidden deep within the Earth itself. He theorized that heat from the decay of radioactive elements in the Earth's mantle creates massive, slow-moving convection currents. You can think of these like giant, boiling conveyor belts of molten rock that could literally drag the continents across the surface. This was the powerhouse engine that Wegener's theory had been missing.
Then, in 1961, Harry Hess took this idea a step further with the concept of seafloor spreading. New mapping of the ocean floors had revealed these enormous underwater mountain ranges called mid-oceanic ridges. Hess figured that at these ridges, hot magma from the mantle rises up, cools, and forms new oceanic crust, pushing the older crust away on either side. This new crust then travels for millions of years until it's eventually destroyed when it sinks back into the mantle at deep oceanic trenches. The ocean floor was a giant conveyor belt.
And all of this came together in the modern theory of plate tectonics. This theory explains that the Earth's rigid outer layer is broken into a series of plates that are in constant motion, and all the action happens at their boundaries. Where plates pull apart, that's a divergent boundary and new crust is made. Where they crash into each other, that's a convergent boundary and old crust gets destroyed. And where they just slide past one another, that's a transform boundary.
All right, let's bring this global theory home and look at a case study that is incredibly relevant to us, the amazing journey of the Indian Plate. This story explains the very existence of some of the most dramatic geological features on the subcontinent.
Okay, here's the timeline. Around 200 million years ago, the land mass that is now India broke off from Gondwanaland and started racing northwards. About 60 million years ago, it passed over a volcanic hotspot, triggering massive, prolonged eruptions that formed the vast lava flows we call the Deccan Traps. Then came the big one. Between 40 and 50 million years ago, the Indian Plate finally collided with the Eurasian Plate. That continent-on-continent collision crumpled the crust and pushed up the Himalayas. And that collision is still happening today.
This map here gives you a snapshot of that incredible journey. About 71 million years ago, India was essentially a giant island, speeding north across an ancient ocean called the Tethys Sea, with Asia far in the distance. The relentless northward push eventually closed that entire sea, and the sediments that had collected on its floor were scraped up and thrust skyward to become the highest mountain range on the planet.
Now, how do we take all of this fantastic geological history and structure it for the UPSC exam? This is crucial. You have to know the difference between the facts you need for prelims and the deeper analytical concepts required for mains. Let's break that down.
Okay, for prelims, it's all about quick recall of names, dates, and terms. You need to know Alfred Wegener and his 1912 theory. You must be able to define Pangaea and tillite. And you need to connect Arthur Holmes with convection currents and Harry Hess with seafloor spreading. For mains, however, you need to think bigger. You have to explain the evidence for drift, trace the evolution of the theory, detail the mechanism of plate movement, and really analyze the formation of major features like the Himalayas and the Deccan Traps. It's about the why and how, not just the what.
And finally, let's see how this could actually look on exam day. For prelims, you might get a multiple-choice question testing your knowledge of Wegener's specific evidence. The answer here, by the way, is B, because paleomagnetic data came much, much later and was key to proving seafloor spreading. For mains, you'd see a question that demands a more narrative analytical answer. It's asking you to tell the whole story we've just covered. The key to a great answer is explaining not just that the theory changed, but why it had to change. What were the new discoveries that forced that scientific revolution?